Have you ever really stopped to think about how our world actually works? I mean, from the way a massive steel ship just floats there, to how a simple paper towel can soak up a spill, our world is constantly being shaped by these beautiful and, honestly, kind of surprising laws of physics. Today, we're going to pull back the curtain on these invisible architects. Okay, so here's a fun one for you. What do a giant cargo ship, the brakes in your car, a paper towel, and a simple garden hose all have in common? At first glance, absolutely nothing, right? They seem totally unrelated. But as we're about to find out, they're all connected by the same elegant set of physical laws. All right, let's tackle our first puzzle, the ship. It's a question that just seems to defy common sense. How on earth do thousands and thousands of tons of steel not sink straight to the bottom of the ocean? Well, the answer comes from an amazing principle that was supposedly discovered in a bathtub more than 2,000 years ago. And this is the big idea, Archimedes' principle. The easiest way to think about it is this. When you get into a bathtub, the water level rises, right? The water has to move out of the way. Well, that water is also pushing back on you with a force, and that upward push is equal to the weight of the water you just moved. It's the water itself that's doing the lifting. Now, the most important phrase here, the real secret sauce, is the weight of the fluid that the body displaces. It's not about how heavy the object is on its own. It's all about the weight of the water it shoves aside. This is why a giant ship is built with that huge hollow hull. Its shape is designed to push away a massive amount of water. And if the weight of all that displaced water equals the ship's own weight, it floats. Simple as that. And you can actually prove this to yourself with a super simple experiment. Just weigh any object. Then, weigh it again while it's submerged in water. You'll see, it'll seem lighter. That missing weight is the buoyant force from the water. And here's the really cool part. If you were to collect and weigh the water that spilled out, its weight would exactly match the weight the object seemed to lose. It's an incredibly elegant concept. And this ancient idea is at work all around us. It's how submarines fill their ballast tanks with water to dive and push it out to surface. It's even how hot air balloons float. They just displace a huge volume of cooler, heavier air. So you see, the secret to floating isn't about being light, it's about being good at pushing a heavy fluid out of the way. And just like that, mystery number 1 is solved. Okay, so if buoyancy is all about fluids pushing up, our next puzzle is about how we can use them to push out with incredible force. I'm talking about your car's brakes. Have you ever really thought about how a light tap from your foot can stop a 2-ton vehicle moving at high speed? It sounds impossible. The secret is the power of pressure. This is all thanks to something called Pascal's law. The best way to picture this is to imagine squeezing a water balloon. When you squeeze it, the pressure you apply isn't just in one spot. It makes the whole balloon bulge out everywhere, right? That's because the pressure is transmitted instantly and evenly throughout the fluid, while brake fluid in its lines works the exact same way. And because that pressure goes everywhere equally, we can do something that feels a little bit like cheating physics. We can create what's called a force multiplier. It's a way to take a small, weak push on one end and turn it into a gigantic, powerful force on the other. So here's how the magic trick works. On the left, you apply a small force to a small piston. That creates pressure in the fluid. But here's the kicker. That same exact pressure then pushes up on the much larger piston on the right. And since that piston has a much bigger area, the resulting force is hugely multiplied. To see what I mean, let's plug in some actual numbers. Let's say you apply a tiny input force of just 10 newtons. I mean, that's barely anything. It's about the force you need to lift a bottle of water. That little push creates pressure throughout the system. And because that pressure is acting on the second, much larger piston, the output force is 25 newtons. We've more than doubled our strength, basically for free, just by pushing on a trapped fluid. That's the incredible power of hydraulics. This is how a mechanic's hydraulic lift can raise a heavy car with what seems like no effort. And it's exactly how your foot on the brake pedal generates enough clamping force on the wheels to bring you to a screeching halt. And with that, puzzle number 2 is cracked. All right, on to our third mystery. And this one really does look like magic. How can a paper towel make water climb upwards, completely defying gravity? Well, you guessed it, it's not magic. It's a beautiful molecular phenomenon called capillary action. So capillary action is just this amazing tendency for a liquid to flow into really narrow spaces, sometimes even pulling itself up against the force of gravity. The whole process is driven by a tiny little tug of war that's happening at the molecular level. In this little tug-of-war, there are two competing forces. First, you've got adhesion. You can think of this as how sticky the water molecules are to the walls of the tube or the fibers of the paper. Then you've got cohesion, and that's how sticky the water molecules are to each other, the force that makes them want to stay together. And here is the simple rule that decides the winner. If the liquid's stickiness to the walls is stronger than its stickiness to itself, in other words, if adhesion beats cohesion, the liquid will literally start to pull itself up the sides of the tube, molecule by molecule. This is exactly what's happening in a paper towel. It's not one big tube, it's thousands of tiny little spaces between the fibers, and the water is climbing up all of them at once. It's the same incredible force that lets plants drink water up from the soil and pulls oil up a lamp wick to the flame. Our third puzzle is officially solved. And now for our final puzzle, something I guarantee you've done 1,000 times. You're using a garden hose, and you put your thumb over the end. Suddenly, the water shoots out way faster and farther. Why exactly does that simple little action have such a huge effect? Well, just think about the amount of water flowing through that hose every second. When the opening is wide, the water can just cruise along at a pretty relaxed, slow speed to get through. But the second you block part of that opening with your thumb, you're trying to force the exact same amount of water through a much, much tinier space. The only way for all that water to get through in the same amount of time is for it to speed up a lot. This relationship is described by something called the continuity equation, and it's basically a law of conservation. Just think of it like a seesaw. If you decrease the area on one side, the velocity on the other side must go up to keep things balanced. A smaller opening always means faster water. It's a fundamental rule. And this isn't just for garden hoses. This exact principle is happening inside your body right now. It governs how your blood speeds up as it flows from wide arteries into tiny capillaries. It's how air moves through your lungs. It's just incredible, isn't it? The same physics that helps you water your garden is also literally keeping you alive. And with that, mystery number 4 is solved. So there you have it. Buoyancy, pressure, capillary action, and fluid flow. We've seen how these invisible principles connect everything from giant ships to the paper towel on your kitchen counter. It really makes you look at the world a little differently, and it definitely makes you wonder, what other hidden physics are all around us, just waiting to be noticed?